All right, our class sites had a little bit of an overhaul, adding more materials, making the links a little bit easier for you guys to find things, because I've been known to post bad links before. So you have access to the Google Drive with all the shared information right here, as well as the YouTube. If I don't get the playlists updated in time, you can now access the channel without links to the specific videos. I opened up that security a little bit, so I guess I'm now a published YouTube artist. I'm not sure how I feel about that, but hopefully nobody else will be motivated to watch our class lectures. I've also added the beginnings of a page to collect information for your final project, so I'll add the assignments as we build up towards that. I've assigned assignment number 5 today, so we'll touch on that. And I've started to build a map showing some of the locations that I've received so far to help guide you if you're still selecting your area. Though that was due today, I saw a slew of emails come in, so I'll be adding those as I receive them, and hopefully we can cover a lot of interesting areas in this final project. So today's assignment will be to identify at least 3 data sources that you might wish to use in your map. This isn't going to lock you into using those data sources, but I do expect you to find and identify sources that work in your area of interest and download and add them to a map to confirm that there's actually data there that you can use. So that will help us continue to build towards this final map product. So hopefully these kind of backbone steps are not a panic when you go to turn in a refined project. So that's just a little classroom update, maintenance. Oh yeah, speaking of classroom update maintenance, I decided to throw out the lecture on creating GIS data. A lot of the material was redundant to things that we've already discussed, and you guys have been digitizing data for quite a few labs now. Doesn't mean that there's not more information to be learned about those topics, but I felt like the data on, or sorry, the lectures on database querying, attribute tables, and spatial querying was too compacted, too crammed together in one lecture. So I'm going to split that into 2. We'll sacrifice creating GIS database or materials, and hopefully nobody will suffer for that. But I didn't see much information in there that we hadn't at least touched upon. And I don't want to blow up your brains with databases and database theory and how it applies to GIS databases. So that's what we're going to start talking about today. And then next week we'll pick up on spatial querying. I did adjust the reading schedule accordingly, because I think if you are a textbook learner, it will be to your interest to have at least started reading chapter 9 when we talk about spatial analysis. This is actually more of that type of a split. So chapter 9 is on spatial analysis, which is kind of a backbone tool for GIS and deserves its own class. As you've probably figured out by now from the midterm exam and the way that the pace at which we've moved through this class, I don't expect you to read each chapter painstakingly, but I do suggest that you familiarize yourself with the contents of the chapters at the bare minimum and know where to go for additional information on the things I cover in my lecture. I'll hit all the topics that I expect you to learn in the lectures, but I won't necessarily provide all the detail in the slides. So that's what your textbook's there for. It's a resource for deeper learning and for issues you might run into on the labs. Anything I might not cover that Volstead would pick up, since he's both the lab author and the textbook author. This should read lab 5, oops, due today. Lab 6 is due next week. Thursday we'll do Lab 7. As you can see, I was undecisive when I created this lecture on how I was going to change that. There's a little bit of heartache that goes in with throwing out a whole lecture. So starting with geospatial databases, we've talked a little bit so far about geodatabases as a data format in ArcGIS, but we haven't really extensively discussed why they came about, or why it matters whether you keep your data in a shapefile or a geodatabase. Can anybody remember some of the trade-offs between the two? What does it look like when we have a geodatabase format versus shapefiles? So let me see if I can find a good file folder structure. All right, so here's a project where I have multiple geodatabases. And when I look at the file structure for these geodatabases, it's pretty meaningless, right? Like all of this is back-end database language. You can kind of identify where some of the data information is probably stored, but you're not going to be able to look at this and necessarily understand all of the relationships between the items. We have.
Actually, was going to make an appointment with you guys over the phone, and I did it over online.
Hello? Got some background noise there. So one of the disadvantages of a geodatabase structure, kind of from a classic GIS perspective, is the data format itself is a little less transparent. It's housed in this geodatabase structure, and you can't directly interface with it like you could with a spreadsheet table or some other things that we used to use a little bit more in GIS. But we've talked about the trade-offs and the benefits to a geodatabase. So does anybody remember what some of those are?
Well, it's fast to access, and you can minimize the storage if you have a lot of information to handle.
Yeah, those are kind of the two primary powers. So the geodatabase can store far more information than a shapefile, and you can do a lot more powerful data analysis with it. It's better computer science, so there's better storage methods, and more that you can do to both manage and interpret your data. So for a geospatial database, there's a couple of different types you can use. You can still interact with a access database type, but more commonly now we've begun to use these geodatabases with the file structure like I just showed you. So that's kind of the wave of the future. You can see in ArcGIS Pro that they've started to integrate that into every project. Every project automatically creates a geodatabase. Unfortunately, it doesn't automatically put your data into that geodatabase, which is kind of how I would like to see that function. But it gives you the ability to start adding feature classes to that geodatabase a little bit more routinely. And then once we have our data into our project and our database structure, we can start doing a little bit more analysis with our data. And you can do similar analysis with shapefiles, but you start to lose efficiency, and you lose some of the control that you have over that data structure. So we're going to talk about where that begins to matter. So apologies for the slides crammed full of words. I haven't totally pared all of this down yet, but these are the things that a database or any database management structure can do for you. So they store data and attributes of all types. In a geodatabase, it relates it to a spatial structure. And then a database management system starts to control the interactions between those files. So it's going to limit what types of attributes you can apply to your data, right? You've seen a little bit when you create a new attribute, in your attribute table, let me pull one over here, you have some control over what type of data that is. I wish I could zoom this for you, but I can't. So you can control whether it's a text field or a number field. We'll talk a little bit about controlling the range of data that you could input. You could say we're only going to allow numbers between 10 and 50, or things that start with the letter A. So that's what your database management structure gives you in terms of additional power and control with your analysis. So like any data collection system, garbage in means garbage out. So if you can control what comes in, you can improve what comes out of it. So again, the power of creating a managed database structure is that you control the organization of that data. And so you control the flow of information through your system, from the data that we acquired, that we talked about in creating GIS data. So you either went out and surveyed, or you found somewhere online this data and you brought it in, and you manage your data structure in such a way that it's useful for you in your analysis. And the ideal way to do that is through a geodatabase. So database management systems, to some extent, feel like the wave of the past. In computing, database used to be the center of everything. It's a hugely utilized computing system because it allows us to organize digital data. So it's gone through a lot of different waves of theory, but we still essentially rely on this relational database structure that we use in ArcGIS Pro today that was developed in the 1960s.
Can that data be kept in any kind of relational database, or is it?
So that's kind of one of the things with the transition to the new ArcGIS geodatabase format, is that you no longer have that same flexibility that you used to have. You can still open a personal geodatabase using ArcGIS, but you can't go the other direction. So you can't take a file geodatabase, which is the default ArcGeodatabase format now, and go back to a personal geodatabase. So that .mdb format was a somewhat more portable format, I think developed with Access Database. I'm not 100% sure on that. So yes and no, you can open them, you cannot open a geodatabase going the other direction.
Gotcha, thank you.
So kind of the underlying architecture of a database is the database language. A lot of them use SQL as a database language. SQL was developed for interacting with databases, so it has other tools built in as well. It's not something that you're not typically going to get involved with the database language of your geodatabase. It's already been designed and implemented by the software designers, but it's good to have some understanding of what tools might be available to you when you're interacting with that database. One of the neat things that I've seen with ArcGIS Pro is it allows you to, in some cases, select your query language, and we'll get into queries a little bit more later. But if you're more comfortable querying data in one language than another, you have some flexibility with that in ArcGIS Pro. So the language is the structure, or sorry, the language is the toolbox. The data dictionary is the structure. So this is how you design your database in such a way that you can capture all of the information that's important. So every file type, or most of the file types, I should say, that we work with has the ability to capture metadata. So if you look in your catalog view at a shapefile, you'll notice there's these 3 classic tabs, and one of them is to preview the table if there's not too big of a file selected. This handy one is to preview the geography. And then this one that gets heavily ignored is the metadata. For data sharing, this is something that I would love to see populated a lot more than it is. For example, I went looking for a US counties file that had the same data structure, but actually included Alaska, because this is just freaking annoying. We matter too. And unfortunately, I couldn't figure out exactly where this one was identified because there's no metadata attached to it. And I just ended up flailing around on the census database site, and I found this TL 2019 US county, which I was hoping was similar. But it also has no metadata, so it's not the most useful in demonstrating metadata. Anyway, in an ideal world, your files would come to you with metadata ascribed to them. So keep that in mind when you're developing and delivering data sources. One of the best examples I had for this was a geodatabase deliverable that we had for Shell. And it was based on a prescribed format that allows exchange of offshore data. So it's specifically designed for things that have marine elements. So looking at things like your water level datum is really important in a marine environment. So that's built into their required metadata in their database format, because there's nothing worse than receiving a file missing that kind of information and not even knowing spatially how to apply it. So pitch on my part for the importance of metadata. But I'm just as guilty of it as anyone else when I'm just building little shapefiles or feature classes for a working map. I'm not going to go spend the time to populate the metadata for all of those. But I would feel differently about it if I were going to share and deliver that, that data. I would probably want to at least fill in the crediting authorship information so they knew where to come for questions. And then information about your spatial data is always really helpful to users in case a projection file gets separated, things like that. Or if they want to know how the data was collected and how accurate they can assume it is. That's a good thing to store in your metadata. So using a geodatabase structure, we can control the data entry. And we're going to get into some of those tools today. The report generator is not something that I've used very heavily, but documentation of a database is always something that you will wish you have done if you don't do it. Because it's the whole point of a database system is this somewhat more complex system of data management, and it can be really easy to forget what you're doing if it's just something that you're going to use within your own projects. But if you're sharing it, it can be really difficult for other people to figure out exactly how your data is linked and how to utilize those tools that you've built in. So documenting that can be really helpful. And then you can also control your means of update. And we already talked a little bit about using SQL as a query language, so we'll look at that a little bit today in class and then in our lab. So we've looked a little bit at attribute tables. One of the reasons that we use geodatabases is to accommodate more data in an attribute table. So it's not just, the size of your shapefiles or the number of shapefiles that you have, but also the amount of data that you have in the background behind that. So a lot of the shapefiles that we looked at early in this class didn't have a whole lot of attribute data applied to them, but more often than not, the data that's stored in the attribute table in the files that I use is more important or more dense than the shape. You know, I might be talking about a bunch of little squares and have a lot of data attached to that. You can imagine, like in a property database, you have all the property lines, and those lines and boundaries in themselves store a fair amount of data, but there's a lot of data that can go into the back end that can provide information to the users about property values, ownership, history of management of that data set. So all that gets stored in attribute tables. And we're going to look a little bit more at the structure of how those link with your shape information, your spatial data, and then also the tools that we can use to control that. So when we talk about databases, table is a fairly straightforward idea to hopefully all of you. Just a means of organizing your data. So your columns provide your field structure. Anything that goes into a field has to meet certain requirements, whether it's a number or a text or the number of, what's the word that I'm looking for? The number of digits that you can have in your text is all controlled in your rules for your table when you set that up. Characters, that's the word I'm looking for, not digits. These are letters. All right. And then your rows would be your records. So each spatial feature has a record that applies to it. That's in spatial data. In a table, you might have multiple entries referring to a single logical entity. So we'll talk about the different types of ways that we join that information together in order to make this database structure. And then the index or the key is how we figure out how all of these relate to each other. So this is a fairly common database structure for a spatial data set. We're going to talk more about these unique ID numbers. So in a GIS system, this is usually referred to as a feature ID or FID. I think in ArcGIS, yeah, you're typically going to see that appear by default as the FID or FID, feature ID. A lot of spatial data sets will have geometry fields built in. And these can either be, I don't want to use the word stagnant, but fixed so that they don't update, or they can be tied to the feature itself, where they're not directly editable, but they are directly related to the geometry of the feature. That takes a little bit more background processing power, so you lose some efficiency, but you know that they're always up to date that way. And then you can have whatever attribute data comes along with that. So we'll talk a little bit about different types of data. So the feature ID, although it's auto-generated by ArcGIS, is just a number field, and it's specifically an integer. So we're going to talk about the difference between integers and other types of numbers, which are floats and doubles. And then you have the other common field type of text. So when you build your table, you define the data that people can enter. And there's a little bit more precision that you can apply to that, in that you can specify the type of number, for example, that people are allowed to use. So these, I still find myself, after close to 20 years of playing with databases, having to go look up the difference between a float and a double, and what exactly is the limitation on a short and a long integer. But these are really handy pieces of information to at least know where to go and look and remind yourself, oh yeah, okay, so that's what a float does, and that's what the limitation is on a short integer. But essentially, an integer is a number that does not allow a decimal point. So you can't divide the integer data entry into fractions. And part of the should say limitation or structure of a database is that there's a sacrifice of storage space that goes along with each of these. So if you define a number that you plan to have be 1 through 10 all the time, like you're never going to have anything but 1 through 10, and you store a long integer, you have now sacrificed twice as much storage space for every feature, whether or not you put data in that feature, as you would have for a short integer, for very little gain. So if you end up with 50,000 entries, that's twice as much. So you're using, at that point, I'm not good at these computations in my head, something like 200 megabytes of data that you didn't need to expend if you had used a short integer. So similarly, with the float and the double takes twice as much storage space as a float, and a float field takes the same amount of storage space as a long integer. So the double is twice again that, and both of those allow you to have decimals. So when they say floating point numbers, you could have a number that was 2.147483, or you could have a number that was 2147.483, and both of those would take the same amount of storage space. So the in a geodatabase format, the precision and scale of those, so that's when we're moving around that decimal place. So the precision tells you the total number of digits that you can have, and then the scale defines how many of those digits are allowed to be a decimal place. If you use a geodatabase, then you don't need to define these in advance. That number can flex. But if you use a shapefile, you do need to define precision and scale when you create that field. So if you decide later, if you start out only collecting 3 decimal places and you decide you want to enter a number with 4 decimal places, you won't be able to. You would have to create a new field and copy your data over, probably is the most efficient way to deal with that.
To what extent do floating point errors occur, or do they?
I'm not sure that I've ever seen errors arise from it. More inconvenience of not thinking it through fully ahead of time and having to repeat or recreate some steps. I don't know if that fully answers what you were.
Yeah, I was just getting at, like, certain decimals can't be represented truly or accurately, right? So I didn't know if that had caused a problem in some of these databases, like, I don't know, whether it's leaving gaps in between polygons and things of that nature is basically what I'm asking, but it sounds like if you haven't encountered it, then no, not really.
Yeah, so this doesn't necessarily apply to the spatial relationships, just to the attributes. So it would depend to some extent on what type of attribute you're trying to capture and how much that level of precision is important to that attribute. And I haven't seen a lot of instances in this type of data where I care much beyond, 3 significant digits. I guess if you were getting into, say, like a statewide geochemical database, some of that could come into play a little bit more. But I would say on the whole, for data sets of this type, I'm either defining integers or a float feature. And then it's really nice to have the convenience of not predefining my precision and scale, though it can end up a little messier. It's nice to know when I'm entering a data set of survey data that's been collected, if I've defined a scale as having 3 decimal places, I know that nobody's going to try and pretend that they've measured to 4 or 5 decimal places in the field, which is typically something that should cause you to raise your eyes at your surveyor. So having that predefined data management kind of caps that understanding of the level of accuracy that's actually been achieved. All right, and then our other attribute entry types are text, which is fairly obvious and straightforward, though there are, I think, let me just confirm, since I have it open, some different types of limitations that you can put on your text fields. So we're initially limited to 255 characters. That's a pretty universal database text size limitation. And I don't see it in the initial data type offerings, but I think there's a way now to attach larger text fields. There's also ways to embed some simple imagery, but we're not going to get into any of that. And that's, I think, mostly done through different like third-party tools. So not something that ArcGIS is really set up to support, but it is a flexibility of certain modern database structures. I know in Access, you can attach images to database records now, but I wouldn't call it the most useful or versatile tool. There's better ways to manage that outside of the database structure. We talked already about feature IDs. Those are automatically assigned by ArcGIS, and they are a unique identifier for each feature that you draw. So you can't change your feature ID, they're automatically assigned. If you delete something and you have a gap in your records, you'll never be able to fill that in, which is something you should just learn to ignore, because the sole purpose of that feature ID is tracking that information kind of through the life cycle of the database. The idea is it never changes. And then to build on that idea, we have what are called global identifiers. And this was a concept developed as we started to share database information more broadly. It allows you to create a unique identifier. I think in Access, those IDs are something like 25 digits long, and they can choose from a certain range of special characters and then alphanumeric characters. And it basically generates a randomly selected number that has something like 1 in 50 million chance of being repeated. So the idea is you can match up data systems and never repeat a global identifier, hopefully, unless you have really, really bad luck. So what that prevents is, or what that allows is tracking that feature across a lot of different database systems and knowing that just because I've imported this table and it's now auto-generated a bunch of new feature IDs, I'm still going to know where that feature came from because it has this unique global identifier that's following it around. And I think that's something that ArcGIS Pro doesn't do natively, but there are tools available that you can, I think you can run. One of the geoprocessing tools will assign a GUID to each of your features. And then the last piece of feature data that ArcGIS applies is this shape attribute that tells you the type of shape that is associated with this. And this is something that I don't actually understand from a database theory perspective. You would avoid adding an attribute to a file that only has one answer, right? So we've defined this feature class as a polygon. It's not able to hold anything but polygons. So why do I need to identify for each entry the fact that it's a polygon? And that's something that's done by default when you create this file in ArcGIS. And you know, it doesn't make sense that they would do it for no reason. So I suspect that it has something to do with improving efficiency of some of the workflows that happen within ArcGIS. You can imagine that a lot of the processes that you're going to run on any given data set is going to be heavily dependent on the type of data that you're inputting, right? You can't split a point in half. So there's no reason to have the split function work on a point, because you're trying to essentially produce an outcome that's physically impossible. So it would be really confusing to your spatial data system to try to figure out how to split an infinite point. So I believe the reason that these are attached at the root of the file is to improve the efficiency of that type of spatial identification. But that's just my speculation. Haven't yet identified a reason for including this field information in a table. So from a database management theory aspect, that one's a little bit of a puzzle and I find it interesting. But not something you guys need to worry about. It's just there. I think that's a good place to take a little break. Does anybody have any questions on any of the information that we've covered so far? So we've talked about database management structures, what goes into a database, and we're starting to talk about how they're organized. So does everybody feel comfortable with those underlying concepts? I don't have paired X, you have to use your voices or your fingers.
So far.
All right.
Of course, I think when you ask about it, though, then we'll see.
Yes. All right, everybody take a 5-minute break and we'll come back at 4:49.